After learning the derivatives of hyperbolic functions, it's now time to study their integration. And we know integration is the reverse process of derivative. Here we have listed 6 basic integration formulas which are derived from the derivatives of hyperbolic functions. We already know the derivative of hyperbolic sine, hyperbolic cosine, hyperbolic tangent, hyperbolic cosecant, secant, hyperbolic cotangent, and their derivatives are these functions. We have seen the derivative of hyperbolic tangent is hyperbolic secant square. So integration of hyperbolic secant square is hyperbolic tangent plus c, just the reverse. We will add one arbitrary constant to each function in integration. So c are arbitrary constants. So these are 6 basic integration formula for hyperbolic functions. Using these basic formulas, we can find integration of all other functions involving hyperbolic functions. So let's do some couple of examples. First we know in integration, if integration of small fx dx, let's say this is capital Fx plus arbitrary constant c, then the integration of, in place of x, if we have some ax plus b, a linear function, a, b are real numbers, this integration is capital F of x plus b whole divided by a, and this constant, this is arbitrary constant. Here we just divide the constant multiplied with x, or the derivative of ax plus b. We have already seen this in integration. So in first, if we have the integration of hyperbolic cosine and 5x minus 3, let's say, in place of x we have 5x minus 3. So by this, what is in the integration of hyperbolic cosine? We must know the integration of small f. We know hyperbolic cosine integration is hyperbolic sine, and the inner part will remain as it is. What we will divide? We will divide the derivative of 5x minus 3, or the constant, and our arbitrary constant. Next, let's find the integration of hyperbolic secant square. Here we have let's say pi x minus 2.5 dx. Here also we know the integration of hyperbolic secant square. It is hyperbolic tangent. But in place of x, we have a linear function of x. X is multiplied with a real number and added with a real number. So this is simply hyperbolic tangent with pi x minus 2.5, and we divide it by the constant multiplied with x, which is pi here, plus arbitrary constant capital C. Next, let's find the integration of hyperbolic tangent dx. See, this integration is not covered in the basic integration formulas which we have seen in the starting of this video. So we have to apply something else. How to find this integration? By definition, what is hyperbolic tangent? It is hyperbolic sine over hyperbolic cosine. And here we will apply a method of the integration which is substitution. So we shall apply substitution, and we have to substitute something. We will substitute hyperbolic cosine as t. Let's say t is our hyperbolic cosine, and what is its derivative? dt over dx is hyperbolic sine. So dt is hyperbolic sine times dx. Thus this integration becomes, this upper part is dt, and what is hyperbolic cosine? It is t. This is a basic formula from the integration. What we have? We have this integration as ln absolute value of t plus arbitrary constant c. What is t? We have taken hyperbolic cosine as t, So this integration becomes this one. But now we know hyperbolic cosine is always positive. So absolute value of any positive number is the same thing. So we have ln simply the hyperbolic cosine x plus c, because hyperbolic cosine is always positive and its modulus is the same thing. So this is the integration of hyperbolic tangent. And similarly, let's find the integration of hyperbolic cotangent. Now the integration of hyperbolic cotangent. Here also, what is hyperbolic cotangent? It is hyperbolic cosine over hyperbolic sine. We will do directly. We will substitute this one as t. So this is dt. But the derivative of hyperbolic sine is hyperbolic cosine. This is not trigonometry. In hyperbolic functions, we have the derivative of hyperbolic sine is hyperbolic cosine, and derivative of hyperbolic cosine is also hyperbolic sine. It's not negative hyperbolic sine. So its derivative is this one. If we will take this is t, so this is dt, then integration of dt over t, which is ln of the t is hyperbolic sine plus c. But hyperbolic sine can be positive and it can be negative also. So its modulus can't be the same thing. So the integration of hyperbolic cotangent is logarithm of modulus hyperbolic sine plus c. Now let's do another example. Suppose we have hyperbolic cosine cube times hyperbolic sine dx. Here also we will substitute t, and what is our t? T will be hyperbolic cosine. So this is dt. Dt is hyperbolic sine times dx. We have to figure out whose derivative is in the integration, and that one we will substitute as t or u or any variable, then other is dt. So this integration becomes, this is t cube, this is dt. From the basic of integration, we have the integration of t cube as t to the power 4 over 4 plus c. And what is t? T is hyperbolic cosine x. This is to the power 4 over 4. Now let's find the integration of hyperbolic sine square dx. Like in trigonometry, how we do the integration of sine square x? We used to convert sine square x to cosine 2x using trigonometry identity. Here also we will do the same thing. We will convert this one to hyperbolic cosine 2x using hyperbolic identities. In hyperbolic identity, what we have? Hyperbolic cosine 2x is 1 plus 2 sine hyperbolic square x. But in trigonometry, we have 1 minus 2 sine square x. Cosine 2x is 1 minus 2 sine square x. But in hyperbolic identity, we have this as 1 plus 2 sine square x. From this, we can find what is hyperbolic sine square x. So 2 hyperbolic sine square x is hyperbolic cosine 2x minus 1. Thus hyperbolic sine square x is divided by 2. So 1 over 2 hyperbolic cosine 2x minus 1. So this integration becomes 1 over 2 hyperbolic cosine 2x minus 1 dx by this identity. 1 over 2 can be taken outside of the integration. This is constant. So the integration of hyperbolic 2x minus 1 dx. Next. This one will be the individual integrations. Yes, minus integration 1 dx. So what is this integration? This is not square, this is 2x. Integration of hyperbolic cosine is hyperbolic sine, and this is the linear function of x. So this is 2x plus 0. So you will have 2x divided by 2, and this one is x. Integration of 1 is x plus arbitrary constant c. So this is the integration of hyperbolic sine square dx. Similarly, if it is given that find the integration of hyperbolic cosine square, then also you have to convert that to hyperbolic cosine 2x, then find the integration using hyperbolic identity. Now let's do one example of integration by parts. We have x times hyperbolic sine x dx. See, here we can't apply substitution or any hyperbolic identities, so we have to apply integration by parts. What integration by parts says? Integration by parts, it says if you have two functions u and v of variable x multiplied together and you want to find its integration, you have to keep u, then multiply that with integration of v dx, subtract that by, in bracket we have one big integration where you have u dash, then integration of v dx. What is u dash? U dash is the derivative of u. So this is integration by parts, but you have to choose which one you have to take u and which one you have to take v. In most of the time when we have hyperbolic sign, we will treat that as v, we will integrate that one. So here our u will be x and v is hyperbolic sign, so this is v dx, the integration of v dx. What is the integration of hyperbolic sign? Let us do directly. This one will be u is x times the integration of hyperbolic sign, which is hyperbolic cosine, then minus derivative of u. You have taken x as u, the derivative of x is 1, times the integration of v, this is v. What is its integration? Its integration hyperbolic cosine, then dx. So we are left with hyperbolic cosine x times hyperbolic cosine minus 1 times this one is hyperbolic cosine, its integration is hyperbolic sine, plus arbitrary constant c. So this is the integration of x times hyperbolic sine. See, you have to do the same methods, but here you will apply the basic formulas of hyperbolic sine and hyperbolic identities. Now let's find the integration of e to the power x hyperbolic sin x dx. When there is an exponential function e to the power x or e to the power minus x is multiplied with hyperbolic sign, so it will be easier if you expand the hyperbolic sign. So what is hyperbolic sign? It is e to the power x minus e to the power minus x divided by 2 multiply e to the power x, e to the power x times e to the power x, that is e to the power 2x. Exponents will be added, x plus x is 2x minus e to the power x times e to the power minus x, that is x minus x, which is 0, whole divided by 2 dx. What is we can take 1 by 2 outside, so we have integration of e to the power 2x minus 1 dx. So this is just integration of e to the power 2x. E to the power 2x is e to the power, integration of e to the power 2x is e to the power 2x by 2, and integration of 1 is x. So we have the integration of e to the power x times hyperbolic sign. So you can find the integration of functions involving hyperbolic functions in this way. Sometimes you have to apply substitution, integration by parts, or some identities of hyperbolic functions, or you have to expand. So this is the way. If you have any questions, you can ask in comment section, and I will try my best to make another video on those questions. Till then, thank you.